Those little dents are not decorative, and they are not accidents of manufacturing. They are precision aerodynamic engineering, and without them, the modern game of golf would be physically impossible. The discovery arrived by accident in the mid-1800s. Early balls molded from gutta percha, a rubbery tree resin, began life with smooth surfaces, and they flew poorly and erratically. Then, players noticed something strange. Balls that had been nicked, scuffed, and battered through rounds of play actually traveled farther than pristine new ones. The roughened texture was somehow rewriting the rules of flight, as ball makers began carving patterns into surfaces on purpose. What looked like damage was in fact an aerodynamic upgrade. The scuffs were manipulating the thin sheet of air that hugs the ball as it moves, changing how and where that air peeled away from the surface. Every dimple stamped into a ball today is a direct descendant of those battered, better-flying gutta-percha spheres, and the principle they revealed remains one of the most elegant counterexamples in everyday physics. To understand why dimples win, picture the invisible layer of air clinging to the ball as it flies, a film aerodynamicists call the boundary layer. On a smooth ball, this layer separates from the surface early, leaving behind a wide, churning, low-pressure wake. That wake acts like a parachute, dragging the ball back and bleeding off speed and distance with every yard. Dimples flip this script entirely. Each tiny crater acts as a turbulence generator, deliberately tripping the smooth airflow into a thin, turbulent boundary layer. This may sound like a disadvantage, but the turbulent layer clings to the ball's curved surface far longer before letting go. By delaying that separation point, the dimples shrink the trailing wake dramatically. A smaller wake means lower pressure drag, and the payoff is enormous. A dimpled ball experiences roughly half the drag of a smooth equivalent. Here is the part that genuinely surprises people. Adding texture, adding apparent roughness, makes the object more aerodynamic, not less. The reduction in drag is so severe that engineers gave the underlying transition a dramatic name, the drag crisis, the point at which a sphere's resistance abruptly collapses as its boundary layer turns turbulent. Modern balls exploit this with surgical care, carrying anywhere from roughly 380 to 450 dimples of varying diameters and depths. The diameter-to-depth ratio, the surface coverage, and even the shape of each crater are all tuned to squeeze maximum carry from the same swing. Drag reduction explains distance, but it does not explain why a well-struck ball seems to hang in the air, defying gravity longer than it should. That magic comes from spin. When a club face strikes the ball, it imparts backspin, sometimes several thousand revolutions per minute, and that spinning motion conjures a lifting force from thin air. The mechanism is called the Magnus effect, and it works through pressure. As the ball spins backward while moving forward, it drags air faster over its top surface and slower beneath. Faster moving air exerts less pressure, so a pressure difference develops between top and bottom. The higher pressure underneath pushes upward, generating genuine aerodynamic lift that counteracts gravity and keeps the ball aloft. This is the same family of physics that lets a curveball curve and a spinning soccer ball bend around a wall. Wait though, because spin can also betray the ball. Under a narrow band of speed and spin, the lifting force can reverse direction entirely, a genuinely bizarre phenomenon known as the reverse Magnus effect. It happens when the airflow on the retreating side of the ball stays smooth and laminar, while the advancing side turns turbulent. The mismatch shoves the separation point forward and flips the force downward, pressing the ball toward the ground instead of holding it up. Slice a modern golf ball open, and you find not a uniform rubber sphere, but an engineered system of nested layers, each tuned for a specific behavior. At the heart sits the core, a high-energy rubber compound built to compress violently at impact and snap back, converting the club's energy into ball speed. Around the core, designers wrap one or more intermediate mantle layers that transmit and shape that energy, controlling how the ball responds to different swing speeds. The genius lies in how these layers cooperate. Hardness is deliberately graded from the inside out, with the core softer and the surrounding layers progressively firmer. This gradient lets a single ball reward both the gentle touch of a short pitch and the violent collision of a full driver swing. The covering is the final, decisive layer. A soft cover grips the club face and generates high spin for control near the green, while harder covers spin less and reward raw distance off the tee. This is why cover material matters so intensely. Softer urethane blends deliver the feel and stopping power that skilled players crave, while firmer ionomer resins offer durability and extra distance for everyone else. The journey to this engineered marvel spans centuries of trial, error, and accident. The earliest serious golf ball, the feathery, was a hand-sewn leather pouch crammed with boiled goose feathers. A skilled maker could produce only a handful per day, making them so costly they kept golf an elite pursuit. They flew remarkably well when dry, but were fragile, easily ruined, and wildly inconsistent from one ball to the next. The gutta percha ball changed everything around 1848, slashing costs and democratizing the game, and it was on these balls that the dimple revelation first emerged. Then, in 1898, came the leap that defined the modern era. Winding rubber thread tightly into a ball produced astonishing bounce, and adding a cover created the rubber-wound design that gave ordinary golfers a sudden bonus in distance off the tee. For decades, this wound construction, with its soft balata cover, reigned supreme, prized for its feel. The golf ball you tee up today is the accumulated residue of every accident and insight before it. The synthetic resins of the 1960s, the multi-layer architectures, the obsessively optimized dimple patterns, all of it descends from golfers who simply paid attention to why a scuffed ball flew farther. Genuine understanding often begins not with grand theory, but with noticing the strange, small thing that should not happen, and refusing to look away.